Chemistry, the Central Science, Chapter 6, Electronic Structure of Atoms, Lesson 1. So when we think of waves, we might think of sound waves or ocean waves, but any type of wave is just something that is vibrating and can transmit energy. So there's two major components to a wave: the wavelength, which we designate with the letter lambda, and frequency, which we designate with the letter nu. So two Greek letters here. Wavelength is the measurement between two successive points in a wave, so either the tops or the bottoms. And the wavelength has to be measured in a unit of distance, so we're going to use meters. Your frequency is how many times does a particular wave go through its cycle in a time frame, and we use seconds here. So your frequency is going to be inverse seconds because we look at the number of cycles per second. This is the same unit as hertz. So H-E-R-T-Z, right? A big H, little z. So hertz and inverse seconds are the same. Your amplitude of your wave is simply how high is your wave measured from the midline to the top or to the bottom, right? So that tells you amplitude. And the speed of your wave is going to come from multiplying your wavelength times your frequency. So that's how fast your wave goes. And just looking at these waves through inspection, we can guess that this is a much higher energy wave just by, if you have to trace it, you know you have to move along more than this one. This is a nice rolling wave here. So when your wavelengths are short and your frequency is high, that's going to be a high energy wave. When your wavelength is long and your frequency is low, that's going to be a low energy wave. So the waves that we're going to talk about in this chapter are electromagnetic radiation waves. So electromagnetic waves. What makes them special is that you have both an electric field component and a magnetic field component, and both their wavelength and frequency are identical, and they are perpendicular to each other. So all electromagnetic radiation travels at the speed of light. So in a vacuum, the speed of light is measured to be 3.00 times 10 to the 8th meters per second. So all electromagnetic radiation travels at this speed. These waves are different from a sound wave or from an ocean wave. So whether we're talking about X-rays or gamma rays or visible light or radio waves, that's all electromagnetic radiation. It's like this, right? Electric component, magnetic component. Behaves in this manner such that the wavelength times the frequency equals c, little c, which is the speed of light. So here's our scale of electromagnetic radiation from high energy to low energy. So here on our high energy end, we see gamma rays, which comes from nuclear decay. X-rays, which is why we have to wear a lead apron, and the X-ray tech leaves the room, right? When the X-ray goes off, because it's ionizing energy. UV rays, of course, we know those come from the sun. We have to wear sunscreen to protect cellular damage or DNA damage that comes from these high energy waves. Then we get into the visible region, and then our lower energy waves. So infrared, right? Microwaves, cell phone waves, radio waves, those are all much lower energy because we can see here we have a large wavelength and a low frequency versus over here we have a really short wavelength but an extremely high frequency. Keeping in mind that this times this has to equal the speed of light, respectively. So practicing with the speed of light, a wavelength in a green traffic light signal is 522 nanometers. What is the frequency? So we use our speed of light equation. We know the speed of light, that's constant. We know that it's in meters per second, so that means wavelength has to be in meters and frequency has to be in inverse seconds. So I was given nanometers, which means I need to convert. And I know that there are 1 times 10 to the 9th nanometers in every meter. So I do my dimensional analysis, 5.22 times 10 to the negative 7 meters. I plug that into wavelength into the equation, divide it into the speed of light, and I calculate a frequency of 5.92 times 10 to the 14th inverse seconds. Down here, what is the wavelength in meters of an electromagnetic wave whose frequency is 3.69 times 10 to the 8th hertz? So once again, I use my speed of light equation. Hertz is the same as inverse seconds, so I just write that down. Plug it into where frequency is, divide it into the speed of light, and I find my wavelength has a distance of 0.813 meters. These are the only two things that we can do with the speed of light equation. Why? Because speed of light is constant. So you're either going to divide by a wavelength to find the frequency or divide by the frequency to find a wavelength. That's all we can do. We want to pay attention to our units. So in just thinking about the energetics of waves, we can compare these two and figure out which one is higher energy. So we can either look at the frequency or the wavelength. Here I have a frequency times 10 to the 14th. Here it's 10 to the 8th. Well, this is clearly larger. So this is a higher frequency. I compare my distances, my wavelengths, times 10 to the negative 7th meters. And here I have meters. So this is clearly larger. So I have a larger or a longer wavelength with a lower frequency. I have a shorter wavelength with a higher frequency. So this is clearly more energetic than what this wave is down here. So how do we know for sure that electromagnetic radiation travels in waves? How do we know that light is a wave? So this is called the double slit experiment. So if you just go through one slit, you don't get any type of pattern. However, if we go through two slits that are spaced relatively closely to each other, we see an interference pattern occurring from the light waves. So what happens? Well, we can either have constructive interference or destructive interference. So when the light goes through this slit over here, right, versus this slit over here, when the waves are in sync with each other, or when they are in phase, then we get constructive interference and we see an amplitude then in the wave, a higher amplitude. If when the waves run into each other, they are out of phase, right, out of sync, then they cancel each other out and that would become zero. There would be no light there. So out of phase waves result in destructive interference. So that is why we get this interference pattern of high amplitude, no amplitude, and it's a repeating pattern because of the way that the waves cross with each other and either constructively or destructively interfere. That is why we see this pattern. If light did not travel as a wave, we would not see this. This would not happen. You just see one point on the wall, period. So we're going to look at two different mysteries. The first one is the heated solids problem. So from Max Planck back in 1900, he was looking at what we call black body radiation. So when you heat up a metal, when you heat up an object, it will glow a certain color. We know that if you turn your stove on, your burners will turn red. If you get them really hot, we talk about white hot objects, right? So we see the color red. We looked at the visible light spectrum, right? It's a rainbow. Red has a specific wavelength that is associated with it. If it has a specific wavelength, it also has a specific energy. We know that temperature comes from the measurement of the thermal energy present in an object. Excuse me. So that must mean that the energy that's associated with the temperature and the energy that's associated with the light are proportional to each other. They are directly related. So the hotter an object gets, we can see different colors associated with it, right? Red is the coolest if we're looking at the visible spectrum. As we move towards purple, which would then be our white hot object, we know that that is of higher energy. So basically what this is saying is if you're going to glow a certain color, you're at a certain temperature, you're at a certain wavelength, and these all are discrete units. of what we call energy, and we call those quantum then. So electromagnetic radiation, light, is emitted or absorbed in discrete units, which we call quantum. Now, these little steps, if we think about steps on a staircase, they are infinitesimally small compared to each other. However, when we looked at that green light of a traffic signal, 522 nanometers, 522 nanometers versus 521 nanometers. You're still green, but you have two different energies and two different frequencies associated with those two different greens. So it does go in a stepwise manner. You're either at this energy or at a different energy. It is not a slide. So the equation is energy equals Planck's constant times frequency. And Planck's constant's given down here is 6.626 times 10 to the negative 34th joules dot second. So this is multiplied together. So this just tells us that energy is directly related to the frequency. So how much energy in joules for a photon with a wavelength of 5.00 times 10 to the negative 2 nanometers? How much energy does this give us? And a photon is just simply looking at a particular unit of light, a little packet of light. We'll talk more about that with the photoelectric effect. And then what region is this on the electromagnetic spectrum? So we have E equals h nu, or E equals hc over lambda. This equation was just derived from using the speed of light and Planck's equation, because C equals lambda nu. If I solve for nu, that equals C over lambda. So this just allows me to calculate energy, or vice versa, a wavelength or frequency if I'm given energy. So I look here, I'm given wavelength, so that means I'm going to use this equation. I notice I'm in nanometers, which means that I have to convert. I divide by 1 times 10 to the 9th of my original wavelength. So 5.00 times 10 to the negative 2 nanometers divided by 10 to the 9th gives me 5.00 times 10 to the negative 11th meters. So if I plug that into my equation, E equals hc over lambda, Planck's constant times the speed of light divided by my wavelength in meters allows me to cancel out meters and seconds. I'm left with joules. So the energy for this particular electromagnetic wave is 3.98 times 10 to the negative 15th joules. If we look where this is at on our electromagnetic spectrum, we see that this is in the X-ray region. So extremely short wavelength. If we calculated the frequency, we would see that it was a really high frequency. So this is fairly energetic, right? And we're just talking about one photon, not a mole, right? If we wanted to know per mole, then all we would have to do is multiply by Avogadro's number. So the energy of a photon is 5.87 times 10 to the negative 21 joules. What is the wavelength of this light in nanometers? So once again, we're given energy, we're asked to find wavelength, which means that we want to use this version of Planck's equation. So I identify that my energy is in the correct unit of joules. I plug that in for energy. I plug in Planck's constant and the speed of light. In order to get things to cancel out, I'm just swapping places here. So this times this divided by my energy is going to equal my wavelength. So the wavelength comes out to 3.39 times 10 to the negative 5th meters. If I multiply by 10 to the 9th nanometers, do my dimensional analysis down here, I see that this wavelength is 3.39 times 10 to the 4th nanometers. So comparing back to the last slide that had the X-ray energy, we can see here that this is a longer distance and a smaller amount of energy, or I should say a larger wavelength. So one more, practice with quantum energy. It takes 941 kilojoules per mole of energy to break the bond in N2. So this is diatomic nitrogen as a gas. That should be a subscript. What is the longest wavelength of light in nanometers which will cause this reaction to occur? So if I want to break nitrogen apart and just get some N atoms, how much energy do I need to do this? Or it tells me what energy I need, but what wavelength of light could actually make this happen? And where does this fall on the electromagnetic radiation scale? So once again, I have energy and I want to find wavelength. So I'm using this equation. Now I pay attention to the fact that this is kilojoules per mole, but energy has to only be in units of joules. So I'm going to do a conversion to take me out of kilojoules and moles. I know that in 1 kilojoule there are 1,000 joules, and I know that 1 mole of anything is Avogadro's number. So I perform my unit conversions, multiplying everything on the top, dividing by everything on the bottom, tells me that this is 1.56 times 10 to the negative 18th joules. We may ask, well, what about this photon thing here? When we're measuring energy for electromagnetic radiation, it's always joules per photon, because your photon is just your little packet of light. So now that I have this in the right unit, it is joules. I plug in Planck's constant, the speed of light, and once again, to solve for wavelength, I'm going to multiply these together and then divide by my energy. So this comes out to be 1.27 times 10 to the negative 7th meters. It asked for nanometers, so I convert by multiplying by 10 to the 9th so that my meters cancel out. So I end up with 1.27 times 10 to the negative 7th meters is the same as 127 nanometers, which would be on the UV scale, like the UV range of light. So is nitrogen being busted apart from the sunlight in the atmosphere? Sure, it can. How else would we be able to form other types of compounds up there between nitrogen and oxygen? Think about that. So mystery number 2, the photoelectric effect. So Einstein went off of what Planck had been doing, and he said, okay, let's take a look at different metals. And what happens if I shine some light at the metal? So what he discovered was that at a certain energy of light, that electrons could be emitted. And then if there was higher energy light than what the electrons needed to be released, they would come off with a certain amount of kinetic energy. So we have oppositely charged plates, right? Because we know electrons are negative, so we have to have something positive here to attract them, which then allows us to measure the voltage as the electrical current, and we can change the energy of the light to see, well, what's going to happen. So because of this, Einstein showed that light is both wave and particle in nature. So we call particles of light, we call those photons. And this says that the energy of light is going to be equal to the kinetic energy of the electron plus what we call the work function of a specific metal. So your work function is how tightly is your particular metal holding on to your electrons. So if it wasn't particle in nature and it was just a wave, how would it be able to move something that was solid, right? How would this be able to happen? So it's wave and particle-like in terms of electromagnetic radiation. Now the thing is you have to have a minimum frequency or a minimum wavelength of light here. It doesn't matter how bright the light is. If it's not at the right wavelength, nothing is going to happen. So brightness does not mean more energy, right? That would just mean that you get more electrons coming out or coming off. So you have to have that minimum amount of energy. If you don't, then nothing's going to happen. And where does that energy come from, or what is that minimum amount of energy dependent on? The work function. So if we say kinetic energy is 0, then we know that the energy that is traveling has to equal the work function, and we can solve for frequency. So photoelectric effect proved that light travels in waves, which we proved with the double slit experiment, and then that it is also particle in nature in terms of the fact that it behaves as if it has mass. So practicing with the work function, If the work function of cesium is 3.42 times 10 to the negative 19th joules, what's the minimum frequency of light required to release these electrons from the metal? So, since we don't want to have any kinetic energy associated with it, we just say, hey, this is just to get them out. This is just to kick the electron out, not to have it move with any specific speed after the fact. So the kinetic energy is equal to 0. Therefore, h nu equals W, your work function. So this is right, Planck's constant or Planck's equation that says E equals h nu. So we plug in Planck's constant, we're solving for frequency, and then we plug in our value for our work function. So to solve for frequency, it's 3.42 times 10 to the negative 19th joules divided by 6.626 times 10 to the negative 34th joules per, or joules dot seconds. So our joules cancel out. We have a frequency of 5.16 times 10 to the 14th inverse seconds. So this is how much, or this is the frequency of light that allows us to eject electrons from cesium. So the follow-up question then is, what is the maximum amount of energy in joules that an electron from cesium can be emitted if the frequency of light is 6.1 times 10 to the 14th inverse seconds? So we just keep in mind and we pay attention to the fact that frequency is directly proportional to our energy. So the higher the frequency, the higher the energy. We looked at the last slide and saw that the work function for our metal was 3.42 times 10 to the negative 19th joules. So we plug that in here. We want to know what our kinetic energy is. So we've just rearranged this equation so that Ke equals h nu minus W. So we're given a frequency. We plug that into nu. We know what Planck's constant is. That's fixed. So we multiply these two values together, and then we subtract out the work function energy. And it shows that the kinetic energy of this particular electron would come off with 6.81 times 10 to the negative 20th joules. So this makes sense in the fact that the kinetic energy is less than the work function, right? If this was bigger, then that wouldn't make much sense in terms of how that all played out.